Hello everyone, my name is Cedric Schultz.
I'm Patrick Lindwall.
And I'm Chad Martin.
And we are Group 3. Today we'll be going into DP3 and what we've learned along the way. So, intro to DP3. Basically what we'll discuss in this presentation is our progress plan, what we've done so far, customer needs identification, so what we already established the customer wants, product specification identification, what the customer needs, what we've established in our product, economic analysis, feasibility of that product, intellectual property search, so looking at patents, making sure we're not infringing on anything, concept generation, creating our own idea, concept testing that idea, making sure it's feasible, product architecture, starting to construct that concept and turning it into a reality, and design to manufacture, testing the feasibility of manufacturing that product, and going it more into economic analysis, making sure it's going to turn a profit, and going into the prototype stage, which is basically testing out the real deal. So, first off, identification of customer needs. We took interviews and customer profiles in order to make this. So some of the data that we gathered from customers was it had to be lightweight, easy to assemble, durable, aesthetic, demonstrated an interesting concept for us to teach kids, like something that they would hold on to later on. And so we interpreted that into our own product as no heavy materials, so light things like cardboard, paper, wire, low assembly time, so like 5 minutes assembly time, we can finish it. Let's see, like durability, so making sure like if it's like bumped or maybe dropped from a low distance that it maintains integrity. Things like that, we just translated from what the teacher might want in the classroom to our actual product.
So these are the specifications that we went for when we were building our prototype. So we wanted something that displayed captivating science concepts. That's the potential kinetic energy that we want to give to the students in their lesson. We wanted to have it run for the entire class period, to have it be something the teacher can depend on and the kids can be entertained for a long enough time. We wanted to look good and captivate students. This ties into like a theme and aesthetics and colors. We want it to be assembled under 5 minutes. We don't want it to take up too much time and waste time. We want it to be lightweight so it could be carried in and out of storage by students, by teachers, without any issues. And we wanted to keep the manufacturing costs low so we could put as many of these out there.
Alright, so we did have a few project proposals in the concept generation phase. My product was idea 1, and we determined them. And it was going to have a more customer-first methodology with higher quality but lower sales, but we really work with the customers, get a good customer basis, and hopefully make more profits over time.
Initially, what I had was we were going to have a new product platform. It was going to be designed for 6th to 8th grade students in accordance with the Virginia SOL standards. And it was going to demonstrate motion and energy transfer alongside their science classes.
And so for idea 3, I propose that if we have like a quick product development phase, followed by heavy emphasis on themes and things to grab the attention of students and make sure that that lesson stays in their mind.
So this is the S-curve that was generated from our several project ideas. As you can see, idea 1 does have the greatest profit after a longer period of time. So continuing forward, we did continue on with idea 1, and so far through prototyping it has been working out well for us. We don't know what expected sales will be, but we're optimistic for the future.
So this is our product benchmark. This is where we looked for other existing products on the market that would compete with ours and that we could learn from. So this was a toy we found on Target.com. It's a BRG Robot Factory Challenge. It's essentially a similar idea, but it's not quite executed the way we would want it to. It's not very practical. It doesn't show things really in detail, I don't think. And it looks pretty cheap and like it wouldn't survive in a classroom. But one of the things that we did take away from this is that we wanted a product that was going to be colorful and appealing to students.
So this was our initial cost, revenue, and profit economic analysis, and we had a fixed retail price of $100, which we are still trying to move forward with, and the break-even was $200 parts per year, but this was determined with a $50 variable cost per part. After prototyping and some further analysis, we determined that our variable cost per part was going to be $20, so that would make a much lower break-even but more profits in the end. We also determined that with our manufacturing, it would be more beneficial to increase the amount of products sold, and we do feel that we would be able to sell them. So we are going to expand our parts way past the 500 wrapped here, which will only increase profits. We'll still be able to fit in the one factory, meaning we'll only need $10,000 a year overhead.
So this is a project management that we followed until completion of the project. It has all the tasks in order, concept generation, concept testing. These two are actually paired together, which we found very helpful in completing the project. It would allow us to more properly manage the task completion so we can do more things at once. So that all worked in line, and here we are at the end of project completion. At the presentation of final results, everything has been completed on time. So intellectual property. We did a search of existing patents and expired patents to see what we couldn't do and what we could do by looking at older ideas. So two of the things that we couldn't do were these connection pieces made by Connex and Lego respectively, so we could not use either of those components in building our prototype or our model to ship out. This, on the other hand, was a patent that expired for a manual ramp we could have used in our design if we decided that we wanted to use the servo elsewhere and have this as a sort of user input. This search was helpful at finding all sorts of other ideas that ended up playing into our final prototype.
Alright, so concept generation. Basically, this was the phase where we were coming up with ideas for our product. As you can see, we passed around a few pages to basically brainstorm ideas for what would become our final prototype. To demonstrate like kinetic and potential energy relation, we would have, let's say, a ramp that would lose kinetic energy as it went up and then gain potential, and then it would come back down and then regain that speed, thus converting the potential to kinetic energy. So things like that we experimented with, and this was all to basically get a gist of what we wanted our product to be.
This is our concept selection. So after we came up with each of those separate ideas for each subfunction, we weight them numerically based on their reliability, power, ease of assembly, ease of use, and aesthetics. So we did this with this type of chart for each one, and then we ranked each one based on a 1 to 5 rating for the performance in each category. The best weighted rank for the lifting system ended up being the fan blower. The best for moving the ball was going to be rails and simple foam ramps.
Okay, so product architecture, basically this follows chunking our project down into systems. So some of the systems, as you can see, is like support for the BRG, lifting the ball, user input, track choice, ball movement methods, final ball delivery. So these are all things that we purposefully made very broad. So this really goes into our customer needs and our ability to basically make our BRG very modular, very repairable, very versatile, very upgradable. These are all things that we're really trying to go for while making the system. And as you can see, it's very linear, so we wanted to keep it simple for to build and to keep the assembly time low.
So this is our failure modes and effect analysis. This was slightly changed through the actual prototyping. We determined that the elevator method was not going to work well. It was not reliable enough for us using the fan. So instead we created a ramp, which is described in our CAD drawings. But the selection gate provided to work out well through the prototyping. It did not fail in the way we thought it was going to. It was fairly sturdy and provided more rigidity to the overall structure. And the ramps were coming on a line. This was just a prototype, and it was not an accurate representation because we did know how it was assembled and how to further assemble it, but they were fairly distinct and tactile and going into the boards, so it should not be too difficult to keep the ramps aligned, thus negating that mode of failure.
So these are some CAD drawings we drew during our prototype process. These two are pieces of the final product right here. This is our final BRG with all the components. It has a ramp, or a servo on a turning lever here that ramps down, lets the ball come in and go to the different paths depending on the switch choice by the user. This is that ramp in closer detail. These two are components that were made but later scrapped due to issues with power from our fan. This was made so that the fan would be sort of neck down to the size of the ping pong ball that we were using, so it would have a more concentrated flow of energy to the ball. This was a way for the ball to come into a tube and be shot out by the energy out the other end to another ramp.
So here's our economic analysis. This was created before, but it is still accurate with what we are planning. We did realize that our overall cost for each product was going to be a little bit lower, but we still do think this could be the approximate amount of funds we will need in the beginning and the amount that will be returned later. The values might just be a little higher. There were going to be more manufacturing costs to start with, but with the lower, or manufacturing ramp-up costs, but with the lower cost per product, we don't think we're going to need to ask for more funds. And in the end, we should be able to return higher funds. So here's our assembly time and cost sheet. The only two parts that have to be purchased from outside suppliers are the servo and the microcontroller. The rest is all done through plastic injection molding and through analysis of mold factors and the number of parts that could be printed per mold. We determined that the overall cost was going to be $20.12 to manufacture and assemble for each part. The assembly time is not much, as in all the parts get shipped to the user and they assemble it. The only thing that has to be assembled is the servo and the microcontroller have to be wired together appropriately.
So, testing future refinements. These are changes that we'd like to make in the future before we ship this out to be mass produced. We'd like for the materials to be changed. Maybe there's something that we could create more precisely, like ABS plastic injection molded. We'd like for parts to be more durable. That also goes back to fitment. We'd like them to fit the board better. Everything will line up better. Less chances of failure in each run. We wanted to add more modular features and more features so we can implement our original idea of having interchangeable sub-functions. And we wanted a more aesthetically pleasing design which covers colors, possible themes, and other sorts of things like that would play into the aesthetics of it.
All right, conclusion, I'll make this quick. Basically, we wanted to make a high quality experience for our customers, and we did that by putting a lot of thought and care into everything that goes into that. We had some issues along the way, but our team fixed those. It was finicky, things like that, but we quickly adjusted. But our team is very confident that our product is ready to be manufactured, and we hope you've enjoyed this presentation.